As an example comparing Lagrange and Newton polynomials, we're going to do something a bit atypical. Both of these solution forms can get rather number hungry. Displaying them on screen, especially by my own poor handwriting, whether it's on a Surface or in MATLAB, can get space hungry. So we're going to look straight at a written form and a written example solution of 615. I'll give some notations as we move through the answer. I basically want to show you that figuring these out can be an almost immediate process. So going back to the actual solution, this equation or problem 615, they just give you the form of the data, x and y. So 6 different points for each, and they want a Lagrange polynomial and a Newton polynomial equivalent to both check the values at x equals 5.4. So this is essentially to see which one may give the better interpolation, or if they even give different values or the same values, who knows. So they start with part A, write the polynomial in Lagrange form that passes through the points. So 6 points means a 5th order polynomial. That's going to take a lot of Lagrange. So in each case, if you look back at your textbook in the definition of Lagrange polynomials, which if I can flip back is on page 214, equation 645. That's one with the summation of y times the product of all the x minus xi over xi minus xj terms. This whole mess is what you come up with. Once you know what you're looking at, though, this is repetitive. The leading coefficients, in this case I guess you call them trailing, those are all the y's of the individual points. So notice 2 corresponds there to the y1. 2.8 is y2. 3, y3. 3.2 appears in the right spot. 4 appears there. And then 5, it just follows. So each one of those y values gets its own leading Lagrange polynomial. Everything in the denominator should end up being a number. If you end up with a variable, an unknown x in your denominator, you made a mistake. So in this case, we are doing x of 1 in the denominator, then it's x of 2 in the denominator, then x of 3, x of 4, x of 5, x of 6, corresponding exactly to the same y value. Notice it's 7 minus whatever, 6 minus whatever, 4.8 minus whatever, in every single first term of the denominator. In the numerator, this is where you exclude the point you're working on. So notice in the first term, so y1 is 2, yep, x1 is 1, yep. However, in the numerator, you don't see an x minus 1 term. It's missing. Immediately go to the second. That's due to the fact we exclude all of the polynomial expansion terms where I is equivalent to j. We only multiply together those where I is not equal to j. So in the first term, you skip the first entry. So you do x minus 2.2, x minus 3.4, x minus 4.8, x minus 6, x minus 7. I just read those points straight off the x-axis up here. Not rocket science there. For the second term, notice they do the first. It's present. They do the third through sixth. Those are present. They skip the second. Third term skips the third. Fourth term skips the fourth, etc. Going all the way down until you finally have your entire Lagrange polynomial finished. So look at all that mess. That's why I didn't want to write it out for you. It takes away the simplicity of Lagrange. This is a lot of numbers. Yes, it is very easy, however, to reference them. It is very easy to know where they go, and the form is absolutely repetitive. To spend 10 minutes writing that out by hand and scribble on a surface would undermine this simplicity, even though it looks quite the opposite. So all I've done here in the next step is plug in 5.4 for every open value of x. That's what you're doing with the interpolation. They've asked us to evaluate the Lagrange polynomial at 5.4. So every term collapses down to its eventual decimal form, and we get the output of 3.5116. I mean, is that good? Is that bad? I don't know. I'll have to compare it against what Newton can do. But that there is a Lagrange polynomial, fifth order. To try to even approach a fifth order curve fit in least squares regression would be impossible by hand. This is achievable. If you want to do a first or second order Lagrange polynomial by hand, absolutely, go right ahead. I mean, it's rather easily achievable. Part B, though, Newton polynomial for the given points has the form. Okay, this is the base form of the Newton polynomial, and notice they've just gone in and listed all the different x values. X minus x1 for the first term. Second term has the first and second. Third term has the first, second, third. Fourth term has first, second, third, fourth. And they expand it. Until the time you get to the sixth term, you have everything, 1, 2, 3, 4, except for the last term at 7. Now, this is a single sentence that understates the work required to obtain all these terms. You remember these definitions are starting to get rather large at A3. A4 is twice as big. A5 is twice as big as A4. And it just gets ridiculous as you go on down. That's where this divided difference table starts. And if only it were this small, just taking up this small bottom portion of the screen. But no, it continues. So much so they had to start squishing all the numbers here on the right-hand side to keep it on the page. But let's look here. So 1, 2, 2.2, and 2.8, all of the data is just straight listed in the columns. Then for the first calculation of the second element, they take y2 minus y1, 2.8 minus 2, divided by x2 minus x1, 2.2 minus 1, you get 0.6667. Now look at that. Just from writing things out, you get a1, which is always equal to y1 by definition. So that one's easy. A2, pretty cake, 0.6667. And at this point, you have finished. If you care to do just a straight line curve fit, you're done. That's all you have to do. But now they kind of asked for fifth order, so we have to keep going for a while. So we would step on down and try to immediately do the next term, but we can't. Because it requires we have knowledge of this next step of the second order term, which we only have the first. So you need to finish each column before proceeding on, finish each column before proceeding on to the next one. So this one here, if we can split the difference, because annoyingly that's right at the page break, 3 minus 2.8, so that'd be y of 3, 2.8 is y of 2, 3.4 is x of 3, minus 2.2 is x of 2. So that's, again, just rise over run of the individual data points. You get a value there. And those two collectively feed the third rank. So let's assume you've done all of row 2. Hopefully you recognize that pattern. Let's move on to something in the third rank. Now let's do this very bottom one. So you take the y value in the second rank minus the y value above it. Okay, that's the numerator figured out. But look where the 7 and 4.8 are sourced. You don't go down to the x values here. You go back all the way to the origin. 7, you go back all the way to the origin up here, 4.8. That's true in every case. If you look even all the way up here, what would this be, the fourth rank? If we call that second, third, fourth, that'd be the fifth rank. So the y values are based off of the previous values here. So negative 0.0139 minus 0.0554. And then for the x values, you go all the way down here to 7. And then the 2.2 is sourced by going up the diagonal all the way to the previous page where it intercepts up there, 2.2. So because that's representing a distance, you're essentially taking differences across that whole range from the final point in the series to the second point in the series. And then, of course, the last in the tree will be from the final point to the initial point in terms of x values. So all of this being gone over and scrolling up and down, this is the creation of the divided difference table. It generates this final plot. So this is the same exact equation you had on the previous page. All the x minus terms, which are straight from the initial data, but now you can actually populate a naught, a 1, a 2, a 3, a 4, a 5. And a 6 should, well, I skipped a 5, so, but just start at 1. Yeah, it started at 1. I started at a naught, it starts at a1. And then once you figure and calculate in by plugging in x equals 5.4, and every place the x variable is still shown, this comes out to a value of 3.5116, which curiously is exactly the same value that Lagrange polynomials provided. Should mean that the polynomial fit through these points is unique. It is a unique solution to fit a fifth order polynomial through these 6 points, so each one produces the same interpolated value. So that is an example of both Lagrange and Newton polynomials. Hopefully you didn't mind that was straight out of a PDF example because it simplifies the number soup a little bit. Keep in mind that very shortly you'll have numeric algorithms to handle all these numbers and coefficients for you, but learning the polynomial setup, the patterns involved, and the indices you'll have to program into a computational algorithm is a first step that is very important.